Okay, to finish up this section, we have a theorem we will state and prove, and then a simple corollary that follows. The theorem, called the midpoint connector theorem, says that the segment joining the midpoints of two sides of a triangle is parallel to the third side, and it has a length 1/2 of that of the third side. So here's a triangle labeled A, B, and C. And let's take the midpoints of two sides. Let's take the midpoint of AB, which we'll put right about there, and then the midside of AC, which we'll put right about here, and let's connect them. Okay, what this theorem is saying, well, two things. It says that this segment is parallel to the third side, this segment, and also that the length of this side is 1/2 of the length of BC. And we'll prove both of those. So as it states here, draw triangle ABC. We already have that. Label L and M as the two midpoints of these two segments, AB and AC, respectively. We're going to show two things. One, we're going to show that segment LM is parallel to BC. And two, we're going to show that the length of LM is 1/2 of the length of BC. All right, so here we're going to have to do a little bit of drawing here. Extend LM to a point P. So we're going to extend LM this direction to a point P where M is the midpoint of LP. So basically you just take this line segment and double the length in this direction. I'll say it's roughly about there. So we're going to call that point P. Since we know that's the midpoint, maybe I'll put a little double notch there and a double notch there. We know those lengths are equal to each other since M is the midpoint. Okay, we use the segment construction theorem to be able to create that. All right, here we go. Part number I. Triangle ALM. ALM is congruent to triangle CPM, which we haven't finished this triangle yet, but let's go ahead and do it. CPM. Why are those two triangles, this one and this one, congruent? Well, let's see. We've got a common side length. We have a common angle because these are vertical angles, so those are equal to each other. And then we also have another side. Put one notch there and one notch there. Why do we know these two sides are equal to each other in length? Because M is the midpoint of AC. By definition of a midpoint, this length is equal to that length. So what do we have? We have side, angle, side, side, angle, side. SAS. That's why we know those two triangles are congruent to each other. Okay, so the statement here is that the line PC, this line, is parallel to AB. Why do we know that? Well, it's basically for, I guess, two statements. PC, AB, they're parallel because, let's see, they're cut by this transversal, and we have this angle. I'll put this angle is congruent to this angle. Maybe I'll put 2 there. And why do we know that? By That's by corresponding parts of congruent figures, because this triangle is congruent to this triangle. But what does that mean? By property Z, which actually I'd go this direction, or I could go this direction, we have two lines cut by a transversal. The alternate interior angles are congruent. So by property Z, we know that these two lines are parallel. Now it says draw LC, which gives us another triangle. Okay, there's LC. Label. Okay, I'm going to label 4 angles as 1, 2, 3, and 4. The first angle is going to be LCP, this angle. And I'm going to call that angle 1. The second one is going to be BLC. That's going to be angle 2. CLP is going to be angle 3. LCB is going to be angle 4. All right, so we've got angles 1, 2, 3, and 4. Now the claim is that triangle ALM is congruent to CPM. Oh, we already proved that from up here. But based upon that, that implies that PC, the length, is the same as the length of AL, because those are corresponding parts of congruent figures. Corresponding parts of congruent figures are congruent. And it just happens to be that 1, 2, 3, 1, 2, 3, AL is equal to LB by definition of a midpoint. L is the midpoint of AB, so this segment is half of the length of AB, and so is this half the length of LB. All right, also, we have that angle 1 and angle 2 are congruent. Angle 1, this one, and angle 2, those are alternate interior angles. That is by property Z. And we have that LCP, this triangle, is congruent to CBL, this triangle, because we have a side angle side. Side angle side. Let's see. Yeah. Oh yeah, we've got side, then we've got the angle, and then we've got the common side between them, between the two triangles. So that's true by side angle side. Part 8 will give us that. Let's see. Oh, this is just going to be by corresponding parts of congruent figures being congruent. We can see that LM, which is half of LP, because M is the midpoint, and since LP is the length is equal to the length of BC, we know that these two are equal. And angle 3 is congruent to angle 4. Oops, sorry. Angle 3 is congruent to angle 4. Yeah, that's just additional information. But this is what we were having to prove. LM is 1/2 of BC. So that proves the second part. And then the last part, by using property Z again, we would have that LM is parallel to BC. by property Z. And that proves this. So we've proved 1 and 2, so that means we've proved that this theorem is true. Okay, and last thing is just a corollary, a statement that has to do with this previous theorem we just proved. Parallel bisector corollary. If a line bisects one side of a triangle and is parallel to the second side, then it also bisects the third side. So let's draw a picture of that. If I want a line that bisects this side, has to go through the midpoint. If it bisects it and it is parallel to the second side, say this one, so it would look like this. Okay, this is a line that bisects one side and is parallel to another. Then it also bisects the third side, which tells us that this point is the bisector of this. So again, turns out that both of these lines bisect these lines, segments, these sides of the triangle. If you connect them, it's going to be parallel to the third side. That ends this video.